My apologies. Let me bring that back up. Okay, I hope you can all see my screen. So thanks so much for having me at Embedded Systems Week. My name is Nicolas Fraser. I'm a research scientist at Xilinx Research Labs here in Dublin, having a fine cloudy/rainy afternoon. I hope you're all well in your respective time zones. And today I'm going to talk to you about the co-design of neural networks and accelerators. It's my belief that new performance opportunities are available when you consider both creating a neural network with the hardware in mind and also creating hardware that matches the specific neural network architecture. And so hopefully I can convince you today that that's a good idea. I'll also introduce you to some tools created by members of my team to actually assist you in creating those types of neural networks and creating those types of architectures that you may want to use. So let's get into it. Okay, so I'm going to start firstly with a bit of motivation about the computational demands of neural networks, and that's really the backdrop to this discussion. Then I'm basically going to take you through various points in this stack on the right. So this is basically how we do our co-design approach for this tool that we have called Fin. We train a quantized neural network in Brevitas, in PyTorch, and then we pass that to a compiler that then does some optimizations and generates an architecture that is specific to that hardware. And then we can deploy it in multiple ways, including Xilinx's own Pink device. So before I get much further into it, I probably should do just a little bit of housekeeping about how to run this, how I'm going to run this session. So I have 60 participants, so it's quite a lot. It's quite a lot to have people just chiming in and asking questions. So maybe the strategy that we should take is that I'm going to have various points within this presentation where I'll stop and ask if people have questions on the previous section. At that point, I'm going to suggest that either you put up your hand. I believe this is available in this version of Zoom. And then Ali is going to select you to ask a question. Or if you prefer to just ask your question over the chat, just type it in the chat. And then when we get to those sections, Ali will read out your question. I can't quite really see the chat while being in full screen as well. It's a bit tricky. So I can try to do my best if I can, but Ali, if you can help me out, that would be amazing. Okay, so let's get into some of the introductory kind of material here. So firstly, I just want to tell you a little bit about who I am and a little bit about Xilinx and what sort of devices that we make. So Xilinx is one of the first fabless semiconductor companies, founded in 1984. So that's actually before I was born and potentially before a lot of you people were born as well. Today it has about 4,000 employees and generates about 3 billion in revenue every year. And Xilinx were actually inventors of the FPGA. And so you may or may not have seen in the news that there is a acquisition underway from AMD. So maybe in the near future, you know, I'm presenting vastly different numbers than you're seeing here about a much larger company if things go smoothly, and we hope that they do. So firstly, let's talk about what is an FPGA. If you're just coming to this class and you haven't studied FPGAs before, you're going to struggle without some introduction. For the others, please bear with me for a couple of minutes while I try to explain the basics. So FPGAs are semiconductor devices that consist of a matrix of many configurable logic blocks. These are connected via programmable interconnects, okay? And when I say many configurable logic blocks, we're talking about, on the largest devices, millions of logic blocks, okay? Now, each of these logic blocks is capable of implementing a sort of relatively small logic function. So for example, in modern FPGAs, each of these logic blocks is capable of implementing, let's say, a 6-input logic function. Any 6-input logic function could be 6-input, 1-output logic function could be represented in one of those blocks. There's some other pieces as well, but I'd say that's the core piece that I want to talk about today. Now, modern FPGAs, as well as having these configurable logic blocks and the programmable interconnects, actually have other hardened blocks as well that we can utilize in our design. So these include thousands of DSP blocks. So DSP blocks are pieces of hardware that perform, let's say, integer, multiply, accumulate operations that you're going to see in a lot of digital signal processing applications, filtering and such. They also have hundreds of megabits of on-chip memory called BRAMs or ultra-RAMs. And nowadays, they tend to also contain hardened ARM processors. Often you have a processor that you want to use to control the accelerator and feed data to it. And actually, it makes more sense and it's more efficient to actually harden a processor in there and have a whole bunch of the programmable logic, which is this other region containing the configurable logic blocks and programmable interconnects around it, right? And so if you're not familiar with this, I want you to think about the FPGA as something that we can implement any custom circuit on. So digital circuit on. So if you think about it, right, we have these configurable logic blocks. These are capable of implementing any small input logic function, let's say 6-input logic function, right? Then you have this flexible programmable interconnect, which is deciding how to actually connect those logic blocks together. So you've got something that can implement small logic functions. You've got a bunch of them. You're flexible in how you connect those together. At the end of the day, you can actually implement any kind of logic function that you want using these blocks, right? And then extra things like the DSPs and memories are just ways to get more efficient designs for things like digital signal processing applications. But when you're programming an FPGA, it's a lot more like designing hardware. You're designing a circuit and you're thinking about how logic components connect together. And so today, when I'm talking about designing accelerators, this is what I'm talking about. I'm talking about actually designing a circuit that then gets implemented in the FPGA on these configurable logic blocks with these programmable interconnects. And when we're talking about custom circuits, this is actually a common use case for FPGAs, right? Is that people who are designing, let's say, high volume CPUs and GPUs and ASICs, they will actually first develop their prototypes on FPGAs, which may have slower clock rates and might require more silicon area to make that happen. But then they can actually validate and test and check the performance of their processor, maybe by decreasing their clock rate by a factor of 10, instead of doing something like RTL simulation, which is which is a disaster to get anything that's non-trivial for anything even remotely complex, right? So we're really talking about circuit design at that level. People view these things as blank slates that you can implement circuits on. And so all the accelerators I'm talking about today are accelerators implemented on FPGAs. Okay, so that's the FPGA introduction. I'm just going to tell you a little bit about the group I'm in. So this is the Xilinx Research Labs. I just got a message saying participants can now see my application. Can everybody see my screen just fine?
Yes, looks good.
Okay, great. All right, I just had a small panic there. Okay, so I'm from Xilinx Research Labs based in Dublin, Ireland. The research labs was based around 15 years ago. At the moment, it has 7 researchers plus a very active university program. And at any point in time, we have up to 6 interns, usually working individually with one researcher, 1 or 2 researchers, right? Our basic goal at the moment is to quantify the value of our devices in the space of machine learning. And so this involves creating tools like the tools I'm going to talk about today, developing prototypes, doing benchmarking and creating models and those sorts of things. We very regularly collaborate with many universities and occasionally some industrial partners. And as I mentioned, we tend to have quite a few interns. We have a very active internship program. So I do just want to say from the start, if there's anything in this talk that interests you as a PhD student or a master's student, or sometimes even an undergraduate, get in touch with me after this talk, send me an email, send me your CV, and maybe we can get you on board for an internship. So something to think about while you're listening to this talk. Okay, let's get into the meat of the presentation and start talking about the technical subjects. Before we move on, though, we need to talk about some motivation, and that motivation comes in the form of a problem. And that problem is that deep neural networks, CNNs in particular, have very, very high computational demands. Okay. Now, also, as well as those computational demands, they're very flexible algorithms are being applied to many, many applications, right? So you might have neural networks being implemented in the driver assist in your car, or in audio processing in your hearing aid, and also for something like Google Translate, right? And so these applications have very different use cases with very different requirements, right? So, the energy consumption that you would allow in something like a hearing aid is going to be very different from something that's performing, let's say, translating the web page that you're on or some phrase that you're looking up, right? One is going to be potentially either on a pretty powerful device like a personal PC or in the cloud. One is going to be on something that looks more like a microcontroller that is operating on milliwatts or maybe microwatts or things like that, right? And so from this point of view, it's really difficult to actually generate a single hardware architecture that can actually cover all of these use cases. And in part, this is where, in my opinion, where the FPGA becomes very, very interesting, because of this ability to implement custom circuits that I mentioned. Okay, so as well as having this variety of applications, also there is a general trend towards increasing computational and memory demands of CNNs. And this isn't always the case. You can get things like efficient nets and mobile nets, but in general, as neural networks are being applied in more and more problems, they tend to be getting more complex and have higher compute and memory demands. So this is just a figure that we made up showing, let's say, the inference cost of a whole bunch of different types of neural networks for different applications, and actually just going and calculating here on the x-axis how many giga operations per single inference is required on average to do some type of to do the inference task at hand, and the amount of memory required by the weights of those networks themselves, right? And so you can see, particularly on the right, for some of these speech recognition networks, we're talking about hundreds of giga operations for a single inference. And, tens to hundreds of megabytes of memory, right? And so I do just want to point out a particular example. And there is also a lot of variation, and that's important to note as well. I do want to just point out a particular example. So if we take in the object detection range, if we take a YOLO V2 network which is a little bit old at this point, so it requires roughly 35 gig operations per image for inference to try and detect objects in a particular picture. So if we even modestly, for something like an ADAS application, right, autonomous driving, driver assist, want to implement that at something like 15 frames per second, which I would say is probably the bare minimum, that's 500 of gigaops of sustained inference that your device needs to be capable of delivering. And that's a pretty hard task if you're talking about actually, meeting the power requirements, the thermal requirements, the space requirements that are available in a car, right? We're not going to probably deploy cars with mini servers in the boot filled with tens of GPUs or anything like that, right? Okay, so hopefully I've convinced you of this problem. Now I'm going to talk to you. I'm going to give you a very brief introduction, very high level introduction to Fin, what its purpose is and how we go about trying to solve this problem. And then we're going to break down each of those and talk about them. So Fin is this collection of tools that has been built by myself and my colleagues, right? And the mission is to kind of lower the barrier of entry for people who are interested in machine learning algorithms or interested in FPGAs, and allowing them to relatively easily customize their neural networks in a way that makes sense for FPGAs, and then also deploy them on the FPGA. And so they can actually themselves generate an accelerator, generate a circuit, generate a hardware that goes and implements the neural network that they've trained and go ahead and use it. Now, of course, we're not just interested in lowering the adoption barrier. We also want to achieve high performance. And high throughput and ultra low latency are two of the things that we really, really want to achieve. One last thing I would just say is that Fin is open source. So as opposed to some other solutions that you can find out there by several companies that implement neural networks, if Fin doesn't quite do the thing that you want, you can actually go in there, you can fork the code, you can make changes, you can implement your custom layer, and if you want, you can try to push it back upstream to us, or you don't even need to tell us about it, right? You can do whatever you want, right? And we think this is also a good idea moving forward, right? Okay, so the two main techniques of customization in Fin that we do in order to achieve high throughput, low latency architectures are as follows. So one is we implement custom streaming data flow architectures for specific to the neural network that you're trying to deploy. And I'm going to talk about this mostly in the second half of the presentation. The second thing that we do is that we use custom precision and custom arithmetic without the neural network, and in particular, low bit width arithmetic. And so that's what I'm going to start talking about first. Quantization of neural networks. And so let's get right into it. Before maybe I move on, maybe this is a good point. If there's anything that's not clear so far, if anyone wants to ask any questions.
So I have a question for the Fin open source project. Is it only support the PyTorch and Brevitas learning framework, or it can support a more like learning framework like a paddle, or maybe open source only based on the C programming language?
Yeah. Okay. Good question. And so we'll get into this a bit later, but I can answer this one quickly. So today, what is officially supported and what we support is basically PyTorch with Brevitas. Mm-hmm. But the input to Fin is a custom ONNX format. So basically, standard ONNX didn't quite give us the level of detail that we needed to have about the quantization operators. So we have a custom ONNX format that has some extra information. So if you're able to give a network to Fin in that format, it doesn't care if it's come from PyTorch or Brevitas or anything else. So we are working to try to support some other platforms as well. But as I said, we're a research organization. And so this isn't a massive priority for us, but if it's something that you're interested in, I would suggest maybe getting on the Gitter channel for Fin and see what some other people have maybe done. It could be that your framework of choice is supported there.
Okay, thank you very much.
Yeah. Okay, cool. Let's get into quantization then. Okay, so here, and in both of these sections where we talk about quantization and data flow architectures, I want to, for the most part, I want you to understand and know the background information so that you understand the algorithms, the techniques that's going on under the hood of Brevitas and Fin to maybe go and implement these things yourself. And then at the end, I'm going to talk about a little bit about how you actually go and do this with Brevitas today, which obviously saves you a whole bunch of steps and work yourself. But this may also help you if you wanted to support another framework as a front end for Fin. So again, I'll just bring up this stack that I mentioned before. And in this section of the talk, we're going to talk about this first part. So quantized neural network training, and in particular with Brevitas. Okay, so let's talk about, again, some motivation for why we should even consider quantization of neural networks. Because, you know, potentially floating point seems to work great. It's kind of pervasive and everywhere. Why would we even consider this? So here I have a diagram of a very, very simple neural network, okay? It's got 3 inputs, 3 weights / synapses. It's doing a dot product, right? Followed by a ReLU operation. And all the data types here are floating point 32. Now, this may get you great accuracy in your particular application, although maybe I don't expect this particular network to be that useful. But floating point multiply accumulates, floating point operations in general, fundamentally energy intensive, right? And at the end of the day, this means that it caps your performance and power efficiency, right? So there's going to be limitations that are going to be put in place on your solution that you're trying to deploy, partly due to the arithmetic. Okay, well, we could actually replace these with integer operations. Here, very low bit custom integer operations, which we can do on FPGAs because we can make any circuit, right? I wouldn't want to try to implement 3 bits on a x86 GPU or something like that, but on an FPGA, it makes sense, right? So now the question we need to ask ourselves, and the question I would try to answer next is, if we use this integer arithmetic, what are the implications on the performance we can achieve, the power that we can achieve, and the overall accuracy? So we're going to start with the easiest. So the easiest is power. Sorry, the easiest is performance. Second easiest is power. Sorry. And so here on the left, we can look at it's a little bit old now, but I still have very, very large Xilinx FPGA. And basically what we've done here is we've worked out how many resources you would require to implement something like, on the bottom here, a 32-bit floating point operation, operation being a multiply accumulate, compared with a multiply accumulate that you would get in a binary neural network. And if you pack out the device with those operations, this is what you would get, basically. So you could achieve, let's say, maybe 300 gigaops of peak performance at floating point 32. But if you go to binary operations, it probably doesn't surprise you, you're going to increase that a lot. But it's a 200x increase in performance. So this gets you to 66 teraops of performance, right? Similarly, on the memory side, right, if we're just looking at the weights in the neural network, for this particular device, if we are storing our weights as 32-bit floating point weights, we could fit maybe 2 million weights on chip. And if we binarize those, we're going to reduce this by a factor of 30. You know, we're going to end up being able to store around 70 million weights on chip, right? And so this may mean that actually for our particular neural network we're trying to deploy, our weights may be able to stay entirely on chip, right? And this has some advantages that I'm going to talk about in the next slide, right? So, of course, as you can imagine, reducing precision means reduced power. And so you can think about it in this way when it comes to those configurable logic blocks on the FPGA. You require less blocks to implement, let's say, an 8-bit integer multiply than a floating point multiply, right? And so there's less power that's going to be consumed as switching costs within that, right? So a good example is, so if you went from a 32-bit integer multiply to an 8-bit multiply, you're looking at about a 10x reduction in the energy that's consumed from that. Now, probably the most interesting thing when it comes to memory is that external memory reads can actually dominate your overall energy costs, right? So if you go from something like a read from external DDR RAM to a read from on-chip SRAM, you're going to reduce your energy consumption of that operation by 100x. So this is pretty serious. And so this is something that we take into consideration. And this is partly why for Fin, we're often talking about this extra benefit to quantization, which is potentially storing all of the weights on chip. Now, these numbers on the right, actually, this is from a famous publication about implementing this on ASICs, I believe, with 40 nanometer technology node. So the numbers will be different for the FPGA, but the basic trends and the underlying principles are exactly the same as what you're seeing here. Okay, the accuracy story gets a little bit more complicated. Okay, in general, what happens when we reduce the precision of a neural network is that we reduce the accuracy a little bit. And how much may depend on your particular network and your particular application and how long you're willing to spend to try to train it. But that's not the whole story, right? Because actually, when we reduce the size of the operators, we save so much power, so many resources on the FPGA that you need to actually think about the whole space of accuracy resource trade-offs. So this is what I'm trying to demonstrate here in this figure. So what I've done for this figure is I've trained 3 topologies, YOLO variants, on the Pascal VOC dataset, okay, with different, just going to bring up my pointer, with different bit widths for the weights and activations and a floating point baseline. Okay, I've also included a bonus point here. This is a model that we published a while ago. So tiny YOLO, YOLO 9000, and YOLO V2, right? Now, if you see, in general, you get what I said. As you decrease precision, you lose accuracy. And again, over here, you lose accuracy. Now, that's what I have plotted on the y-axis here. So we have validation accuracy. The metric here is mean average precision. So higher is better here. Now, what's interesting is the x-axis. So the x-axis is we've basically taken a model of the amount of resources that would require you to implement each one of these networks with the arithmetic that we've specified on an FPGA at a given frame rate. So let's say the frame rate is 15 frames per second, as we said before. This is a logarithmic scale over here. So if a model is, let's say, moves in this direction by one of these vertical lines, that means we're going to consume 10 times more resources on the FPGA, which means an FPGA 10 times bigger to achieve that frame rate. Okay, so now when we have this space plotted, we can start to look at some interesting points within it. So what's interesting is, for example, by moving to a more complicated topology, but with simpler arithmetic, we can actually achieve some pretty serious benefits with reduced precision. So the examples, like I've shown you here, we're going from, on the bottom, 2 different variants of tiny YOLO for different precisions. And if we actually reduce the precision to the next level, so here going from 8-bit weights, 8-bit activations to 1-bit weights, 8-bit activations, but increase the complexity of our network. So here, this is tiny YOLO to YOLO V2. We improve our accuracy by 15% for basically the same hardware costs. So basically, no change in the resources required to implement this, but 15% improvement in accuracy. Similar with this model down here, although this is going from tiny YOLO to YOLO 9000, and from 1-bit weight 8-bit activations to 1-bit weight 3-bit activations, right? Some other interesting points. So if we go from tiny YOLO 8-bit weights 8-bit activations to YOLO 9000 1-bit weight 3-bit activations, we can increase the accuracy by around 8% for a 5x reduced hardware cost. So again, that means 5 times less resources on the FPGA to achieve the same performance. So this is what we think is partly interesting about reduced precision. It lets you explore different parts of this space of accuracy throughput trade-offs that maybe you wouldn't have available to you if you just stuck with floating point itself, or even if you went down to 8 bits, which is starting to be relatively standard in the industry for quantization now. Finally, I just want to show you the Pareto frontier. So this is basically each point that's on the Pareto frontier. Basically, you can say that they're not Pareto dominated by other points. So for example, this point here, it doesn't really make sense to go and implement this point here, because if I wanted to use that amount of hardware, I could actually, for the same amount of hardware and the same throughput, implement this point instead, right? And what's interesting is that all precisions except for the floating point actually appear on the Pareto frontier. So if you had a specific accuracy requirement and a really high accuracy requirement, you could maybe take a horizontal line across this graph, and everything above that is something that meets your requirement. And therefore, you probably want to take the one that requires the smallest FPGA, which would be, let's say, this point here. You wouldn't use the floating point one unless you had maybe another reason, like you couldn't be bothered, right? Similarly, on the resource requirements, right, you could take a vertical slice. If you've already selected the size of your FPGA and your target frame rate, you could take a vertical slice and then pick whichever model is on the left of that, which achieves the highest accuracy, right? So hopefully from that, I've convinced you that quantization is interesting. It's something that you want to consider when you're actually designing your system around your neural network, and considering it for deployment, particularly on some embedded space where you may have other requirements than just accuracy. Okay, so next I'm going to talk about the underlying techniques that are used to achieve that accuracy while quantizing your neural networks, and a little bit about Brevitas, our tool that lets you quantize neural networks in PyTorch. Before I dive in, let me just ask if there's any more questions. Okay, I'm going to move on. All right. So quantization in general, it's a pretty simple idea. I'm sure you're all familiar with it. This slide is to just kind of make sure that we're on the same page. So usually when you're talking about quantization, you're talking about taking some original, let's say, real value distribution. For today, we're not really going to, in this section, distinguish between real valued things and floating point things. I'm going to say floating point is close enough. I'm very sorry to all the mathematicians in the audience. So firstly, we probably want to do something like scale this to some range that will map some of these values to a set of integers that we're mostly interested in. Then we're going to round the values in that distribution, and it changes it from this continuous function to this kind of staircase function of a bunch of histograms of different predetermined values, right? And then finally, so here we haven't actually specified the bit width yet, right? Because we've only rounded things, but we could still have potentially, depending on our underlying data type, infinitely many of these values, right? So the last bit is that we need to actually constrain our range to some minimum and maximum value, right? Here, chopping off these edges to actually make it fit in a predetermined number of bits, okay? Now, this is what most of this section is going to be about. It's about how to define the bit width that contributes to calculating Z, how to get an expression for it, how to optimize it, and also how to optimize S, this scaling factor that is used in combination with the bit width to determine basically the trade-off between representing this entire range of original values with increasing the resolution in the middle. And I hope you can all see that, right? So if we actually scaled these values so they all fit between Z and Q, Z and Z plus Q, right? Z and Z plus Q minus 1 for people who are sticklers for 2's complement. We would get the maximum values in this range represented, but we would have less resolution for what's sitting within this range. Okay, and that's a trade-off that we need to make and we need to optimize for when we're quantizing. Okay, so let's talk about different quantization techniques. And here we're mostly going to talk about quantization-aware training, which is a specific technique to achieve quantization in your neural network. And we're going to contrast that against another popular technique, which is known as direct quantization. Okay, so direct quantization basically takes as an input a floating point model, right? It takes a look at the weights and it takes a look at the value of the activations, usually by applying some calibration data. And based on that, it makes some decision on what quantization values it's going to use for the weights and activations, particularly those scale factors, to decide what are the final values that are going to come out. Now, there's a big problem here, in my opinion, and that is that when you're doing inference, you're actually deploying this network down here, right? So you spend all this time, and I don't know how many data scientists there are here. I've dabbled occasionally, right? You spend all this time and effort optimizing your model, coming up with hyperparameters to finally achieve the accuracy that you want. And then you give it to maybe the hardware machine learning guy in your team, and they go, oh, great, I'm going to change all your weight values, and this is your accuracy now, right? And depending on what sort of bit width they use, they could end up with any of the following values that we see on the right. Okay, so this is using something like a classic calibration technique to quantize a ResNet 50 model. Now, we can see that it works surprisingly well for something like 8 bits. You barely get any change in accuracy. But for things like 6 bits or 4 bits, or even something strange like 3 bits, you get this pretty significant, pretty steep reduction in accuracy that happens that may not meet your application requirements. Okay, now there are newer techniques than the one I'm using here. I put these numbers together a few years ago, but the trend is still the same. So maybe with the newer techniques, 6 bits will work for ResNet 50 as well. But still there is some cliff, and it tends to drop off. Now, what we're proposing with quantization aware training is basically retraining, or could be even training from scratch. Maybe you don't even do this step of training a floating point model. Maybe you go straight to a quantized model, right? But the idea is that your optimizer, your feed forward function, all of the layers, your gradient descent calculations are all aware of the fact that when you deploy this network, it's going to be quantized. And what that means is that you get just better accuracy for the same network, right? So if I took these points where I directly quantize them, and I just run a few epochs, a few iterations through my training set of retraining with quantization aware training, I can basically significantly increase the accuracy. And given what we said about quantization allowing you to keep things on chip, allowing you to achieve more performance, in my view, why wouldn't you do this? It could save your hardware engineer months of time to try retraining your network at a lower bit width. So in particular, if you're going below something like 8 bits, retraining helps a lot. Maybe you'll still see a degradation in accuracy. And those examples I gave you on those YOLO networks, they were retrained, just to be clear. But it's going to give you significantly better accuracy, particularly for those lower bit widths, compared to the direct quantization. Okay, so maybe some of you have noticed the main issue that you get into when you're talking about having your backpropagation algorithm aware of your quantization function. Okay, so basically, you probably know that backpropagation is calculating gradients of all of the weights within your neural network with respect to the loss function. So it's calculating partial derivatives of your loss function on the current input with respect to all of the weights in your network. And you hit this point where you go like, okay, now I've got this rounding function in my compute graph. What am I going to do with that? As soon as I apply a rounding function somewhere, this is this staircase function, basically, my gradients are 0 everywhere. So the neural network's not going to train anymore. What are you going to do? So a group several years ago, and with some theoretical founding, came up with this trick. It's called the straight-through estimator. What you do is when you apply rounding on the backward path, you pretend that that rounding function doesn't exist, that it's an identity function that doesn't change anything related to the gradients. as if you're just passing it straight through. And so from a standpoint, you could say, well, now when I'm applying my optimization techniques, I actually have a mismatch between my feed forward function and the gradients I'm calculating. Is that going to cause me problems? And what is amazing is that this actually works. So despite that sort of objection, this works in practical examples, and this works all the way down to something like binary neural networks. Okay, so a practical example like we're seeing on the right. So usually then when you're applying an activation function, you can take this quantization function with this rounding function where you know you're going to use the straight through estimator on the backward path. And you basically convert your previous ReLU function with the composition of the ReLU function and your quantization function. And what you're going to get out is, what you're going to get out is something on the right. So originally we had a ReLU function. Then we had then now we're applying the quantization function after the ReLU function. And this is what our gradient function is going to look like on the backward path. Okay, so the key area here, the difference is that it's going to be clipped at the maximum value. And that's something that we didn't have before on our ReLU function, right? And so it's a trick now. How are we going to actually define values that specify S here and B in order to optimize this function? I mean, I'm sure you could imagine, for example, if you had your S defined as a really, really large value, okay, you're going to have a big staircase function with big can actually draw on my screen. You're going to have a huge staircase function, right? And you're going to represent more of the range of your activation function, but you're going to have less resolution. Alternatively, right, you could have a different staircase function that looks like this, that maybe is very precise within this range, but actually doesn't capture the difference between these large values that you might have during training, right? So keep this in mind. This is one of the key pieces for how to get quantization to work during training. So one is the application of this rounding function with the straight through estimator. The second is to, can you see my annotations, by the way?
Yes.
Okay, great. It just gave me a message like that some people can't see them, but okay, I'm gonna continue on. So first is the application of the straight through estimator to this rounding function. The second is how we select this S value and this B value here in order to maintain high accuracy. Okay, I'm gonna just clear all of that. Yeah, okay, and now I can move on. Okay. Okay, so here's where Brevitas comes in, right? This is the quantization aware training library that we talked about before. Now, Brevitas allows you to, for each layer that's supported within the network, specify the precision, and either as a constant or as a learned value. We're going to talk about how to learn it as a particular value. Whoops. It allows you to specify that scale factor. So that's that S value that we had before. We refer to those as scale factors. Specify different strategies for calculating it based on statistics that are gathered during training. It allows you to specify particular constraints. For example, maybe your hardware implements classic fixed point arithmetic, in which case that scale factor value might need to be a power of 2, or you might achieve a performance benefit if it is a power of 2, right? Compared to some other architectures where maybe this could be a floating point value and we don't mind, right? It also allows you to use the broadcasting semantics within PyTorch to allow your tensors, so like, let's say your weight tensors, to have different quantization formats within one tensor, if that's something that you want to be able to do. It is something we exploit in Fin. It allows you to quantize weights, activations, and accumulators, right? And finally, it also provides a bunch of loss functions that you can use for some of the techniques that we're going to talk about later, so that you can actually take the implementation cost function, like the one that I showed before with these models about accuracy, throughput, trade-offs, into account when we're actually training our neural network. I think this is pretty cool. So there's the link there. It's open source. Go check it out if you want. I'm going to move on because we did start 10 minutes late, so we're running a little bit behind. So the key thing here for Brevitas is to allow you to actually model the reduced precision data path that you are going to use during deployment at training time. And it does this by creating a new set of layers that are quantized variants of existing PyTorch layers in some cases. And we'll talk about the batch norm later, with just extra parameters that you can use to specify all the things that we discussed before: the type of quantization, the bit depth, the scale factors, and how we calculate them. Okay, so here is a very, very basic example, but this is just to give you an idea of what the API looks like. So on the left here, we have vanilla PyTorch implementing a very simple neural network. I'm sure you'll agree. And on the right, we have the Brevitas implementation of the same network, but with 8-bit weights. Okay, so we can just add some extra parameters that we supply, specifying what sort of quantization type this is, which this is the integer type, which is sort of a variant of a generalized fixed point data type with 8 bits, and bam, once we do that, we can train that neural network. All of the other stuff that exists when training a neural network is all the same, but now we're just going to have this extra constraint on the weights. Now, okay, so clearly, given what I just showed you before for the API, we can actually specify the bit width on a per layer level, right? We could have passed different parameters to all of those layers, allowing for heterogeneous quantization of our network. And this is what we're going to talk about next, okay? One final last thing I'm going to say about here is that there's 3 main different types of quantization that are available in Brevitas, which is the binary data type, which is actually a bipolar data type, which we're representing with 1 bit. So we're talking about -1s and 1s here. A ternary data type, and a arbitrary precision integer data type. Cool. And so this is a little bit of marketing about relatively new technique that's available in the literature. But question that we're going to bring up, and hopefully this whets your appetite for the next section, is how do we actually choose the bit widths within our network, right? So here's an example that my colleague Alessandro has done on MobileNet V2, which I don't know if you're familiar with this, but this is a very notoriously difficult network to quantize. So the floating point model is on the right, and its accuracy, let me correct myself, this is now measuring error. So this is error rate on the y-axis. And so lower is better here. And this is the same sort of graph that we showed before with compute cost on the x-axis. So again, lower is better. Okay. And this is a few different examples of quantizing MobileNet V2 with different types of constant precision that are available in the literature. And this is what you get if you use Brevitas to actually learn the precision. Okay. And so in this example, on average, the bit width of the weights is around 2.8. The bit width of the activations is around 2.2, and we still get pretty decent accuracy. And there are those loss functions that I mentioned before allow you to make trade-offs between what this precision will be towards the end and what the accuracy will be. And we'll move things along this in this space automatically while you're training the neural network. So this is the next topic that I'm going to talk about, and this is going to be diving into the weeds a little bit. I see we're just before the hour mark now. Maybe I'm going to give you all 5 minutes because 2 hours is a long time to listen to me speak, although maybe you see I'm passionate about this, so I could do it for much longer. But why don't we take 5 minutes? Everybody go to the toilet, grab a cup of tea. We'll be back. We're going to say it's going to be 10 past 12 in the local time. So 10 past the hour. Okay.
Actually, there is a question in the chat box.
My apologies. I should have asked for questions first. Please go ahead and ask.
Yeah, there's a question from Thomas. Hi, Nicolas. I have a question about your QBNN. Like, you know, the first and last layer are not binaries. How do you transfer binary to full precision at last layer and also first layer? Could you provide some detailed information about your BNN training? Thanks.
Yeah, let me just read that question because there was an example that was mentioned. Okay, so I have some slides that's going to cover this a little bit later. So so the key idea right here is that the first layer, the input to the first layer, for example, may not be binarized. I'm not sure which Quantize BNNs that you're talking about, but we need to when we're going to deploy it. So in many of our examples, so say, for example, the original Fin paper, we had two main examples there, a bunch of implementations on a bunch of networks trained on the MNIST dataset and a bunch that were trained on Cypher-10. So for the MNIST dataset, the dataset is already quantized to 8 bits before we start. And actually what we do is we actually, for that paper, we binarize the inputs. So those networks in those papers, the inputs are binarized, the first layer is binarized, everything is binarized. The last layer is a little bit tricky. So sometimes we binarize it depending on the particular application. Sometimes we don't. I'm going to explain this process that we call streamlining, which basically in part of that process, we get rid of any floating point operations that would appear at the last layer. And instead we're left with integers. So an example is the Cypher-10 network that we used in the Fin paper. And these examples are available online. You can go check them out. I'll continue to provide links. For the Cypher-10 network, the input images are quantized to 8 bits and the weights of the first layer are 1 bit. And then the output of that layer is 1 bit. So it's binary. Then at the end of the network, the weights of that layer are 1 bit, but the results are actually fixed point integers. Let's say integers, we can be more specific. Integers sitting in an accumulator, right? And so this next technique that I'm going to talk about after this little break is going to explain how we get rid of any of those floating point operations surrounding that. Okay, I hope that answered the question. Okay, great. Okay, I'll give you 1 more minute. I'm going to pour myself some tea. So please give me 1 second. just gonna point out, you can't really see it. This is a Turkish teacups from my colleague who is the lead of this Fin project, Yaman Umaroglu. So he gave them to me as a gift, and he would be very upset to see that I have milk in my tea. I'm pretty sure, I think if you do this in Turkey, you get shot or you get deported or something like that. So, okay.
That's a beautiful cup.
Yeah, it's very nice. I just you know, I'm Australian. We usually have our tea with milk in it. I can't help it. I was hoping that it wouldn't be public, but I just saw, now I'm on camera using these teacups. So if anybody knows Yaman, I'm talking about you, Daniele. Don't tell him.
Thanks, Nicolas, for taking this class. This is awesome. And
no worries at all. I'm glad you're enjoying it. Okay, I think I've given you an extra minute, so I think we can get back to the meat of the talk a little bit. So here, we're about to jump down our first rabbit hole. Maybe I should just quickly ask, if there are any more questions before I move on to this next section. So this is about learning the scale factors and the bit widths using backpropagation, something that you can do in Brevitas. Hopefully, I'm going to give you enough information to go and implement this yourself, if you want to do that. Okay, I will push on. Okay, so this is a motivation slide. Listen, I am running a little bit behind time, so some of these motivation slides that I have peppered through this presentation, I'm going to have to be a bit brief on. I apologize for that in advance. So what I want to say here is that deciding on the quantization scheme is still a challenge. So there's actually been many publications showing that heterogeneous quantization of your neural network is actually really, really beneficial, right? So if you look at, so meaning that you can achieve far fewer bits if you allow different levels of quantization to be used in different layers of your neural network, which, as we said before, gives you better power, better performance. But then that brings up a huge problem. How are we going to decide for like this big network? You know, some of these networks have 50 layers, some have 1,000. I haven't seen many with 1,000, but still, it's really, really hard to go and pick, okay, am I going to go through every layer and try to individually tune what I want to use as the precision, right? And most of the proposed solutions that exist within the literature rely on what is generally called meta-learning techniques, right? So meta-learning techniques are something that sits one abstraction higher than training a neural network. So an example of a really, really bad meta-learning technique, we could do a brute force search to decide all of the layers in our neural networks. In our neural network, let's go from binary to 10 bits, go through each individual layer, set the different precision for every single layer, do every permutation, train the network, tell me what the accuracy is, and then I'm going to have a really, really good answer. Other better techniques, well, obviously, as soon as you get to a non-trivial network, you're going to get exponential growth there, right? And it's going to take you extremely long amounts of time and GPU hours to actually go ahead and to do this. Okay, so other techniques that people have proposed are things like deep reinforcement learning. There's one notable paper at CVPR a few years ago, right, where they used deep reinforcement learning to actually optimize the bit widths that they were using throughout the network. But these sorts of techniques, still, you have some deep reinforcement learning algorithm that sits outside the training procedure of your neural network. It's going to estimate in your network a bunch of quantization parameters. Then it's going to go and train the whole network. then it's going to get your accuracy results and go like, oh, that wasn't a great configuration that I've just used. And it's going to update its model, improve its model so that it can make a better estimation of your quantization parameters for the next time, right? So as I said, every internal loop of this is actually going and training or retraining your neural network. Retraining is probably a little bit better because if you're going from floating point, retraining maybe is 1/10 of the number of iterations, but still, this is a big problem. And in general, and well, it's hard to generalize these things, but I'm just going to go ahead and say it. This requires orders of magnitude more compute than training a single neural network. Okay, that's the big problem here. So if you're somebody who has access to a huge number of resources because you're Google or OpenAI or one of these teams, maybe you just go, yeah, deep reinforcement learning. Let's do that. That's great. I'm going to use that to optimize my bit width while it's optimizing all of the other parameters of my network. And bam, done. I'm going to get an awesome compact neural network at the output. For the rest of us, we need something better, right? Now, what we can do is we can actually use backpropagation to actually define the quantization scheme, to define the quantization scheme itself. So I just want to remind you of this equation that I showed before, right? This is a pretty common quantization function that you might use. The previous one that I showed you was unsigned. This one is signed if you're keeping track of the differences, but otherwise it's basically the same, right? We take the input, we scale it, we clip it to some values determined by our bit width. We then round the output and we then provide some post-scaling during training to make sure that basically we haven't changed the range and therefore the training dynamics of the neural network that much. Okay, so what people have used for many years now, maybe about 5 years using this straight through estimator, they have for a quantization function and given some gradients at the output, they've been able to define what gradients there should be at the input. Okay, this is a huge breakthrough. This is how this whole extreme low bit width quantization field started. What we're going to do is we're going to define also gradients for the scale factor and for the bit width here. Now, once you do something like take this expression up here and actually draw it out as a compute graph, and this is what I've done down the bottom. Down the bottom here, I've just taken all of these operations that I have up here. I've separated the clip into min and max functions, but otherwise this is exactly the same. And now we can actually see all of these operations, excluding the rounding function, are actually semi-differentiable. So long as we have gradients that we can define for our rounding function, and we tend to use this straight through estimator that I spoke about before, there's nothing stopping us from defining gradients for S and gradients for B. We can actually just, even if your machine learning framework has automatic differentiation, you don't even need to do the calculations. All you need to do is define a custom operator that implements this rounding function, but has an identity function in the backward pass. And then you just define this expression, but now with your custom rounding function, and you're done. Okay. I'm going to, in the next couple of slides, very quickly go through the calculations and put them up on the screen in case people want to implement this on a framework that doesn't have auto differentiation. But anyway, so it's pretty clear to see, right? If we have gradient here, we can calculate this gradient here. We just apply the chain rule, we're done. All of these operations are semi-differentiable except for this rounding function to calculate gradients for the bit width. And finally, we apply the scale factor twice. So we have some more gradients that are coming out here that we calculate for the scale factor. So our total gradient for the scale factor is S2 and S1. And these are the expressions that you get out at the right. And maybe for the purposes of time, I won't go through them pretty much. But there's an issue with what I've just described here. So one thing is, okay, I've defined gradients for my bit width, but what happens when I use stochastic gradient descent to update my bit width? Now I'm going to have a non-integer number of bits. Maybe, as I said before, we also want to apply constraints on our scale factor, and we actually want that to be, maybe we want that to be powers of 2 or whatever. But all we have to do is then with this graph down the bottom is augment it a little bit. So for the bit width, adding in another rounding operator, which you already know how to deal with the straight through estimator, and bam, we have integer bit width, we have gradients that are calculated for the bit widths. For let's say if we wanted power of 2 scale factors, now we can just add in some extra functions to make sure that we come out with powers of 2, so log 2 and 2 to the power of here. And again, the only one that doesn't have, that's not semi-differentiable is another rounding function. We already know how to deal with it, right? And so again, if you've got, if you're using a framework that has automatic differentiation, all you need to make this happen is to calculate a custom rounding function and to use that when you're calculating this expression, and you're done, right? So I'm just going to give you some results. I'll try to be a little bit brief because there's still a lot more I want to get through today about what you can achieve in quantizing with Brevitas. We've had a recent focus on 4 bits. So a lot of the models that we've been looking at are 4 bits everywhere, in some cases, except for the first and last layer. What I do want to point out is that with the exclusion of this ResNet 50, all of these models here are actually, you know, so-called efficient models. And these, if you're not aware, are notoriously difficult to quantize. But actually, with using Brevitas and using these techniques to calculate scale factors and things like that, actually you can achieve very, very high accuracy, very, very high accuracy relative to the original. And cool, that's all I'll say about that. Let's kick on a little bit. So the very last thing, I want to show you a quick model definition of how you might define something like a model that you would actually use with Brevitas. So here's an example of a 3-layer multi-layer perceptron with binary weights, binary activations, okay? And I'll just go through some of the parameters that we're using here. So we're using the binary quantization type. We're using our scale factor. We're calculating from statistics, and we're using the average magnitude. So that means if we take all of the weights in that layer, we calculate the absolute value of those, then we take the average. Those weights will now be the a bipolar value of that average floating point value of the weights. So it's still 2 values, but they're floating point numbers. On the activation side, which is doing plus or minus 1, and we're using a constant scale factor. So I'm not actually optimizing the scale factor using any of the techniques that I said before. And in Brevitas, you have options, right, to do these things. Now, one last thing I wanted to bring up, and I think this is partly what the previous questioner was asking about, were things like batch normalization in your neural network. So how do you actually deal with things like that? So here I've defined this network, and you can say, okay, let's assume the input is binarized or something, but then we take the output here and we run this through these floating point functions, and then we take the output. Lastly, I just want to mention, in order to consume this model with Fin, we export it to this custom ONNX formats that I talked about. We do need an extra parameter which defines the quantization of the input. I suggest you go and look at some of the notebooks that we have in the Fin repo. In particular, there's a good example, the end-to-end cybersecurity example, that shows you how to set all of that up. I won't spend too much time on it today. So in conclusion, right, for this section, quantization Quantization enables you to make accuracy throughput trade-offs in your network deployments. The quantization parameters themselves can be optimized using backpropagation and the straight-through estimator. Brevitas is an open source library implementing all of the techniques that we've described here, plus many more that I couldn't get to allow you to train a neural network deployed, targeted towards a specific data path. Go and try it. It's on GitHub. You can be set up in minutes. Pip install Brevitas. Go. Cool. Now we're going to move on to the next subject that I was hoping to be at 20 minutes ago, but that's okay. Do we have any questions at this point?
Hi, hello. Can you hear me?
Hi, Hugo. How's it going?
Yeah, good, thank you. I've been actually trying to work with Brevitas and Fin for a couple of weeks
Okay.
as part of my my PhD, and I noticed that there are a couple of functions or operators that you can define in Brevitas that are not very compatible with the export to the Fin model. And
Yes.
I haven't found so far a documentation or a resource where I could find like a list of or precision on the what can work with Fin or what works with Fin and what doesn't. Do you know? Could you or maybe afterwards just point out if you have something like that?
I can try to answer that question as quickly as I can.
Yeah.
So yes, that is a problem. So in particular with Brevitas, there is little documentation at the moment. And Brevitas is capable of doing modeling. The goal is to be able to model any sort of reduced precision data path. So that includes Fin, but it also is a superset of what Fin can do. It can also model the data path for other processes. Now, I would say your best bet is to if the question is about compatibility with Fin, maybe go onto the Fin Gitter channel or make a issue on Fin. You're right on the boundary of whether I say create an issue on Fin or on Brevitas. You're correct. The documentation isn't great at the moment. Probably the best way to learn about how to create Fin compatible quantizers at the moment is purely by looking at examples. The issue that we have here is that Fin is mostly a single person effort. And the API is still relatively unstable. We haven't hit that version 1 yet. And so he has demands to improve the operators and implement new features while changing the API. At the same time, should he spend time documenting the API that's going to change for the next release? So he's kind of in a no-win situation there. I sympathize with your frustration. So, but I would say we're very responsive to issues. So if you don't get a response for the issues, you can email me directly. So that's, nfraser@xilinx.com. So try the issues first, and the guys who create it will help you out. If not, I can certainly help you out.
Okay, thank you very much. I mean,
Yeah.
I'm not. I'm not putting any judgment here. I mean, I realize that it's quite a huge work, especially if it's all year for someone, a single person. I mean, and so far it's already. I mean, from what I've seen, it's already a really precise and big tool. And so yeah, I mean, no worries. Thank you.
I'll pass that on to the developer, and don't worry, I didn't take any offense by your comment.
Okay.
Sometimes I still have to ask the developer, hey, how do I do this again? There's a couple of things and sometimes the API will change He's usually pretty good at updating the version numbers for when he changes API, but I would say when you get something worth working, it's worth making a note of which tagged release you're using and things like that.
All right.
It's still unstable. Yeah. Okay.
Thank you.
Good question. I'm glad I was able to, I hope we're able to help you out. Okay. I'm going to push on. So we're going to talk about the next part of the stack, which is this part, which is talking about optimizations that we're making to, for a start, we're going to look at that network that we've just described, and then how we go about generating the hardware. And I'm going to finish off by showing you then how you can apply all of those steps that we just, that I'm going to explain in this first section in Fin. So Fin makes it quite easy, but first I want to explain actually what's under the hood. So you understand what sort of optimizations in this section we're applying to the neural network to make it more amenable to hardware, what sort of hardware we're generating and how we're generating it and how we're making choices about that. And then the last bit is how you actually use Fin to do it, which is hopefully pretty quick. We are running short on time, so please forgive me if I skip over something quickly. I'm probably going to have to, I was allocating about 40 minutes to this last bit, and I probably only have 30 minutes left. I don't want to eat in too much into your lunchtime. So, okay, so let's start with this model definition that we had before. I hope you recall, that's where I was planning to give you the 10 minutes break. This is why I'm using this slide twice. We have bipolar values for weights. We have that are scaled using the statistics. I'm actually missing a line there. We have bipolar -1, 1 values for the activations. And we have these batch norms. So I want to take a look at just a chunk, like from this quantized hard 10H function to this quantized hard 10H function, and talk about how we optimize that. So, so this is the pattern that we've kind of made here, okay? So we have on the left, we have bipolar inputs created by that hard 10H activation function. We have scaled bipolar values for weights, and these are real valued scales. So these are potentially not very nice. We have a bias creating our fully connected layer, our binarized fully connected layer, with a floating point or a real valued bias. Then we have batch normalization. Now this applies a linear transformation, but it's something that when you're training a quantized neural network is really, really helpful. Like I would definitely suggest putting a batch normalization layer, particularly when you're talking about extreme low precision before every activation function. Okay, but these parameters, these were just the standard PyTorch parameters. These are all floating point or double or whatever we specified as our underlying data type in PyTorch. And then we had that hard 10H function. Actually, we can represent it as a sine function here. So basically converting the output back into those bipolar values that we had. So this kind of looks like a bit of a problem. I mean, I spent that time telling you before how great it is to use low precision arithmetic, and it's going to save you so much hardware. But at first glance, when you look at this, it doesn't look like you're saving that much, right? So, okay, you're doing bipolar multiplication between some values and floating point values. Okay, so maybe they're not as bad as a real floating point multiply. You can do some sign bit optimization there. But now you're adding up all of these floating point values and adding a bias. Now we have a floating point division. This all seems like a bit of a disaster. It seems like, if my intuition as a hardware designer is that actually the main problem is in, let's say, the implementation of this batch normalization layer. This looks horrendous to me, okay? So of course, we don't actually want to implement this. We want to do a bunch of optimizations, a bunch of lossless optimizations. Now I'm saying the word lossless, and what I'm saying is it would be lossless if we're not using floating point arithmetic. Okay, so if we pretend that changing the order of operations in floating point arithmetic is a lossless transformation, then this is lossless. I just want to clarify that there may be changes that you get when you do this process, but they're likely to be very minor. Okay, so here we have the complete forward function on the right, the composition of all of these functions down below. Okay, so what I want to do is I want to create a new function that gets the same result, but actually uses simpler operators that are easier to implement in hardware. That's what I want to do in the next set of slides. Okay, so first of all, we can look at this batch normalization function. Now, all of these parameters we know a priori after we've trained our neural network, except for this actual input here, X, okay? So of course, we can do some transformation here to actually turn this into just a linear function, okay, where tilde gamma and tilde beta are defined as follows. Now, I'm not going to go through where these expressions come from. I hope you can rearrange this and see where they come from here, in the interest of time. Okay, so this gives us a new batch normalization function that is identical, again, using the definition of lossless I used before, to the original one, right? So we've got rid of that division, got rid of a few other functions. I've got rid of a few other operations, which saved us operations, floating point operations, but we actually have the same function. The next is that the bias could actually be absorbed into the batch normalization, right? So we can take this bias here. We can actually define two new functions, right? So now we're actually changing the fully connected function, but because we're changing it in a linear way by subtracting this constant bias, apologies, and adding this constant bias to the batch normalization function, we can come up with a new expression for the batch normalization function so that the composition of these two functions remains the same. And so that's what I'm putting at the bottom here, right? So we just saved ourselves another floating point addition. Okay, what else can we do? Actually, these scaled values can now actually be absorbed into that batch normalization as well. Okay, I'm not going to take you through that. Hope you can see that. So now our fully connected function has changed. Our batch normalization function has changed. What we've done is we've just basically divided the output of this function by, what did I use? Alpha, and multiplied the output of this by alpha, okay? Finally, we can actually merge all of these parameters in the batch normalization function into this threshold, okay? So I hope you can see that if, for example, at the end of this batch norm, if I'm adding beta to the end of it, right, I could instead just use this threshold to be at negative beta. That would be the equivalent of adding beta and comparing with 0, or not adding beta and just comparing with that threshold, which happens to be negative beta. We can also then divide it by gamma, right? And so now we had this complicated function that we had before with all of these floating point operations. Now we've just converted it into bipolar values, an accumulator, a low bit width accumulator potentially, and a thresholding function. And we can even go one further. We can get rid of these bipolar values and we can replace them with zeros, and we can actually use the XNOR operator to actually calculate that multiply. Okay, so this is basically what we call streamlining. And I want to now compare with the original. So the original, we had this batch norm. We had scaled values on the weights. We had all of these floating point operations, this bias, this division over here. And with this lossless transformation, we have converted this into XNOR, low bit width sums. You could do this with a pop count, depending on what your particular network looks like, and a thresholding function. And so Hugo, I suspect if you're having trouble defining a network that is compatible with Fin, it's probably because you're using some combination of layers that doesn't allow Fin to do these transformations. So this is something that happens at the beginning of one of the early transformations within Fin is this process that we call streamlining, which allows it to be more hardware friendly, right? We've just gotten rid of a whole bunch of operations. Okay, cool. So this is a set of techniques that we can apply, and really we're taking advantage of linear transformations that we can apply in the network, and the power of sort of this thresholding function, which actually allows you to hide floating point operations, right? This accumulator, this sum function now is actually fixed point integer values, in fact, right? There's no floating point values represented here. We can also extend this to low precision operators by having multiple thresholds. I'm not going to do that today. Okay, I'm going to move on to the next section. Any questions before I move on? Okay, I see there's some stuff in the chat about me dropping out maybe for a little bit. Apologies for that. I hope you can mostly hear me. Okay, I'm going to push on. I might have to skip a few parts of this next section. I want to get some of the key concepts away, but I might have to skip a particular section. I don't want to eat into your lunchtime, or I know there's multiple people in multiple time zones. So we just talked about streamlining, and now we're going to talk about this last part of the customization in Fin that we use to achieve high performance. And so the last part is the streaming data flow architectures that I mentioned, right? This is a particular way of designing an accelerator. It's something that we use in Fin to achieve high throughput and high throughput versus resource constraints trade-offs, okay? This is what this next section is going to be about. Okay, so in general, most deep learning accelerators, AI accelerators, GPUs, products that are related to machine learning, they look like what you have on the left, which is what we're calling matrix of processing engines, MPEs. Fin and a few other products do what we're doing on the right, which is a data flow architecture. I'm just going to go through and briefly describe what I mean by both of those. Okay, so matrix of processing engines has something like a very parallel set of processing elements capable of implementing dot products very quickly. And that animation wasn't supposed to happen right now. Maybe something's bugging out. But basically what you do is you take your neural network, and this could have whatever, 1 layer, 1,000 layers, whatever. And then you schedule the operations in each layer in your neural network across this matrix of processing engines. So if you have a 3-layer neural network, you're first going to calculate the results of layer 1. Then you're going to store that in memory. Then you're going to feed that as the input for the next layer and load up the next set of weights. Then you're going to calculate the result for layer 2, and so on and so forth, going through the network until you have your final result, right? So this is really, really good for flexibility and to be able, with relatively simple hardware, be able to support a wide spectrum of neural networks. But for specific use cases, this is going to hinder your performance. So one thing is that it's really hard to take advantage of custom precision here. If you want to have, pardon me, if you want to have each layer support a custom precision, you are going to have that one matrix of processing engine support multiple precisions, which increases your resource overhead. If you if you want to have your networks, if you want them to be implemented really, really quickly, you're going to make this single matrix of processing engines really, really parallel. It's going to have lots of multiply accumulates in it. And what happens if you have a really, really small layer in that network? Well, it's not going to use the available parallelism that you've allocated for this MPE. And so it's going to underutilize that, and it's not going to be as performant as you think it should be. An alternative, and this is what we do in Fin, is we implement a data flow architecture where we actually mimic all of the layers in the neural network as a circuit in the FPGA itself. So each layer in the neural network gets its own accelerator within the FPGA. And then we allocate resources based on the amount of compute required by that layer. So this is really interesting in the sense that you don't have what we call one size fits all costs, like I mentioned before. And something's happening with the animations, but you don't have those one size fits all costs that I mentioned before, right? Where you have a very, very small layer, basically, and you're trying to process that on a very, very parallel processing element. You can adjust to every layer individually. When you want to run inference, in this example, you basically just push images through the accelerator and you get the result out the other side. You don't have to do this loop back approach of constantly maybe going back and forth to external memory, right? So this gives you improved efficiency. It gives you fixed low latency. It allows you to customize precision in every layer. But it does mean that basically if you change something in your neural network, you probably have to generate a new accelerator. So this is what I'm talking about when we talk about co-design. The first bit is designing the neural network, designing the quantization, setting up a bunch of layers so they're streamlinable, so they can be implemented with simple hardware. And now we're generating a neural net, an accelerator specific to that neural network. Okay, so it probably doesn't make sense if you're gonna, like, every hour or two update your neural network and trying to regenerate a new piece of hardware to deploy. But it does make sense in situations where, you know, you've got some embedded piece of infrastructure like a camera or something, and you want to do whatever object detection on that. For ADAS is a good example, right? This is going to be one model. It's not going to change very often. Maybe you're going to do firmware upgrades later. Okay, so just to expand on this, I quickly mentioned everything. So the neural network topology is actually mirrored within the FPGA, as I said before, with the weights implemented on chip, hopefully, and the resources actually used in a way that's tailored to each individual layer. So for example, here, we could have 8-bit weights, 8-bit activations used in the first layer, and we could actually use the DSP resources in the FPGA for that layer. While, whoops, what did I just do there? Sorry, I think I hit end, pardon me. Okay. Whereas in the second layer, we could implement those arithmetic operations using LUTs. And by that, I mean those configurable logic blocks that I mentioned at the very start of the presentation. Now, of course, you do need to specify the amount of parallelism, and you need to have that match your specific layer in order to ensure that this pipeline doesn't stall. So for example, if each of these layers were able to do the same amount of operations per second, the first layer is going to execute 20 times faster than the second layer, right? We don't want that. We want a balanced pipeline. Okay, so I'm just looking at the time. I have 10 minutes to go. So I might have to skip over this section where we have a closer look at the hardware. Basically, the main part that I wanted to get across is how we're defining levels of parallelism. Within Fin, we have these two terms, SIMD and PE, which define basically a matrix vector product and the size of that matrix vector product that we're doing in every cycle. And so in this example, we're doing we have a folding factor of 4, which means we compute the output in 4 cycles. Okay, and we can control this by changing the level of parallelism that's available. If we set SIMD to 10 instead of 5 and PE to 8 instead of 4, this would have a folding factor of 1. If we went the other way, this would have, you know, a much higher folding factor and also use less resources. And this is something that we're capable of doing with Fin. So I might move on to just giving you a very brief introduction to Fin itself and talk about some of the key results. And apologies, we will have to go through this very fast. I still have 20 slides to go in 10 minutes. So before I move on, I should just quickly ask again, any questions about anything that we discussed so far, in particular about data flow architectures?
I have a quick question, if you might answer it. Can you hear me?
Yes, I can.
My question is that usually in those data flows architectures, you have to store like big models and you have to access a lot of weights. Are you using the internal VRAMs of the FPGA, or are you having like register banks? Because sometimes I have a problem to, you know, fetch enough weights in a certain amount of time out of the memory. So if you could address that, I would be glad.
Yeah. So that was I was going to address that on a slide I kind of skipped over. So I would say for the most part with Fin, we are trying to target the sort of networks that will fit all on chip. So if you have a network with 1,000 layers and it has hundreds of megabytes of weights, that's not going to fit on chip, even if you binarize them. Fin probably isn't a good accelerator generator to use for that particular network. This is probably more about, I would say in general, smaller networks that maybe fit all on chip. And when I say on chip, there's a bunch of resources. You mentioned a few of them yourselves. You've got LUT MEMS, you've got registers, you've got BRAMs. Okay, depending on the constraint, we could use all of those resources. We generally use HLS and let HLS decide which resources it actually wants to use. But we can also specify that explicitly for particular layers and things like that. And we do have support. I don't know if it's hit the master branch yet, but I think it's in the development branch, support for actually retrieving, for some larger layers, retrieving weights from DDR RAM. So you have all of those options. I would just say the one caveat is that if you are retrieving weights from DDR RAM, you might have non-deterministic throughput and latency now, whereas usually with the models generated by Fin, it's deterministic. The last comment that I will make is that if you're trying to achieve ultra high performance, so let's say your folding factor is 1. So this means every clock cycle you complete a complete inference of your neural network. You complete one prediction of your neural network. It processes an entire input. Then things like BRAMs and UltraRAMs are not that useful because basically you need to retrieve all of your memory every cycle if you're going to do that, right? You need to retrieve all of your weights, all of your any intermediate buffers that you have every cycle. So in those cases, often things get mapped to LUTs. Okay, and if there isn't any more questions, I will push on. So again, Fin mission, okay, lowering this end-to-end barrier, allowing you to specify different algorithms and different quantizations, custom quantizations using Brevitas, and flexibility on what architectures you generate, right? So controlling the parallelism of your architecture, allowing you to actually at architecture generation time to make those resource cost throughput trade-offs that I was mentioning before. And it's all open source, and that's great. So the first stage in Fin is basically what I spoke about before. It's this streamlining step. it's this part of taking all of the linear operators within the network and combining them into something that's a bit more hardware compatible. And then this next step, we lower that into actually the sort of compute that the hardware does. Unfortunately, I skipped over those slides and I apologize for that. But basically all of these transformations happen on a ONNX IR, right? And it's all, again, open source, and you can make changes to that and validate intermediate outputs and do things like use Netscope to actually print intermediate outputs, which is very useful in debugging, right? There's 3 basic steps in Fin. So this importing and streamlining transformations that I spoke about before. The next is where you're actually specifying the inference constraints of your hardware, and then you're finally generating the IP and possibly drivers, right? So I'll just talk a little bit about how you specify this performance next. Now at the back end, okay, we have a HLS library, which is a C++ library with lots of templates, which is how we're able to scale this performance by getting Fin to actually generate the template parameters to determine the parallelism when we instantiate components in our HLS library. Cool thing is this is C++, so it's relatively easy to read. You can get in there and you can try to understand it and you can make changes yourself. Fin can automatically adjust the amount of folding that you're doing. And probably the best way to do this, and I'll show you a quick example later, is to actually specify a throughput constraint that you want to meet. And then Fin will actually adjust how many clock cycles it will take to process a particular input to actually decide how many resources to use. And so long as you don't put in something that is crazy for the particular device you're using, you'll get something that matches that performance. And what you get out is basically this stitched IP that has axis stream interfaces that you can drop into your existing basic design pipeline or into a larger product. You can also generate Python drivers for Pink, right? Which is quite easy to use. I'm not sure if you're familiar with Pink. This is great work done by some of our colleagues in the research labs and in the Xilinx University program to allow FPGAs to be accessed more easily from Python. So we can also generate Pink compatible drivers that allow you to do something as simple as the code that you're seeing at the top here to actually talk to the accelerator that you've created and feed it some NumPy inputs. There will be probably a slight performance hit from trying to do this, but in terms of putting together demos or trying to understand how stuff works, getting something that works end to end is really great. We have lots of collaborations with universities and the community is growing. I really encourage you to go and get on our GitHub and GitHub channels and start using this tool. So quickly just wanted to show you the sort of code that you need to do to take a model like the model that we described at the top there and actually generate hardware. So if your model is already compatible with Fin, and Hugo hit on some issues there that may pop up, you can actually use this Dataflow build config to generate a set of out-of-the-box transformations that will work for most designs, right? And in here, you can do things like specify your clock frequency. So here, 100 megahertz, specify your target frames per second. So here, 1 million frames per second, your target device, and whether or not you want a Pink driver, and so on. My suggestion is if you want to try this, is to go check out Fin, and go check out, there's a end-to-end example on cybersecurity that's in one of the examples there. And it's going to take you through actually all of the steps that you need to build the hardware. But this is the main bit. It can be as simple as this. Generate this config, put in some specifications related to the performance that you want to achieve, and then call this function to actually go and generate and synthesize the hardware, right? Then you can There's a few more steps to actually load it up on the Pink Z1, but that's copying files around and doing that sort of stuff. Going to talk to you, we're going to maybe go 1 or 2 minutes over, and I apologize for that. I do just want to talk about this showcase, because I think one thing is that often what's talked about in neural networks is image processing, computer vision, and Fin is probably better at a different scale of applications. And so one is something like trying to detect malicious packets, or packets that are generated by malicious actors within networking infrastructure, right? So for example, if you're creating a switch or a router or something like that, you are retrieving the packets at the layer 3 of your network interface, right? And you can put this through some traffic classification thing, and it will quickly compute the output. Now, in order to achieve the bandwidth of modern networking, right, you would need to be able to do 150 million requests per second to meet, let's say, the demands of 100 gigabit per second line rate, right? And this is also pretty latency sensitive. So just going to go through this very quickly. So this is the big difference between having a matrix of processing engines and having a data flow architecture, right? So if you use Xilinx's product solution here, this is designed for a sort of different scale of neural network. So it underperforms for this particular example, where you have something like a 3-layer multi-layer perceptron. It's capable of 22,000, it's capable of 22,000 inferences per second, achieves pretty high accuracy with 8 bits as the data type. And here we have the same network, by the way. And we're talking tens of microseconds of latency, right? Compare this with Fin, and let's look at the one on the right. We've gone down to 2 bits, custom precision, same network. We lose a little bit of accuracy. I'm going to call this negligible and skip over the discussion. But we can achieve, basically, by implementing a folding factor of 1, and a 300 megahertz clock, we can do 300 million inferences per second at 18 nanoseconds of latency, right? So we're talking about 1000x, actually in that particular example, 10,000x improvement in performance and 1,000x 1,000x decrease in latency by going to Fin, going to a custom architecture. And it can still fit in a relatively small device. I'm going to skip over the other examples and just go to my summary now. So in summary, with co-design of neural networks, you can achieve new performance accuracy trade-offs. And it's my hope, actually, that this enables deep learning in new domains. We talked about several techniques to implement quantized neural networks, to design, to streamline networks and implement, let's say, data flow architectures. You can also use our tools, which will help you do this in a very simple way, Brevitas and Fin. Brevitas letting you train highly accurate quantized neural networks with backpropagation. Fin letting you generate DNN accelerators and explore throughput resource cost trade-offs. I highly recommend you go check it out if this sounds interesting. The link's down there. This is all open source. Thank you so much for having me. Any more questions before I go?
Yeah, thank you. And I know you sacrificed your tea for quite long. It must have become cold.
It's very
but
cold.
This was an awesome class. Thanks a lot for doing this and taking your time out.
You're very welcome. Happy to do it. Thanks everybody who attended, and thanks yourself for organizing as well. I hope some people found it useful. A few good questions, so I hope those people get in touch.
Yeah.
Okay, thank you. If I have a further question in the future, I can send an email to you.
Yep. I would suggest, if it's related to the tools Fin or Brevitas, you're probably better off going to GitHub issues or the Gitter channel for Fin first, because you probably get a faster and better response from there, to be honest. But otherwise, you can email me. Yeah.
Okay, thanks.
Okay, I think we can stop recording this now.